very 2D pattern. You can see here, along 90 degrees, it is having maximum directivity. Reverse side, you have minimum directivity. You have major lobe and minor lobe also. Any antenna you cannot have without minor lobe. So definitely minor lobes will be there for all the antennas. So this is for the entire 0 to 360 degrees. Next one, we are plotting the azimuth pattern alone. Azimuth pattern for different elevation angle. If elevation angle is 0, what is the azimuth? Elevation angle is 30, what is the azimuth pattern? If elevation angle is 60, what is the azimuth pattern? So slowly you see it is like figure of 8, and then it is becoming an ellipse, and finally it's becoming a circle. So it is slowly transforming as you change the elevation angle of the antenna. Okay. So now I am going to plot the pattern on a rectangular plot. Rectangular plot means I'm going to plot the angle versus directivity. So you have directivity is a periodic structure, right? So you are going to see the angle versus directivity. You can see at what point directivity is maximum. Maximum directivity you have at 88. Sorry. Maximum directivity you can have at 90 degrees, right? So 90 degrees you have maximum directivity. Again at 270 you will have maximum directivity. So this is the directivity. I'm plotting it in rectangular. Rectangular means you have x-axis and y-axis. X-axis is the angle, and y-axis is going to be the directivity. Okay. And how to plot multiple frequencies. We are going to plot the response of antenna over a range of frequency in the same graph. You see, over the frequency variation, what is directivity and the elevation angle we have got. See the result here. We have plotting a three-dimensional graph. I'm varying the frequency from 400 megahertz to 300 to 400 megahertz, and I am plotting for the entire elevation angle from 0 to 360 degrees, and I'm plotting the radiation pattern of the antenna. So you have a plot style. If you use plot style, it will display a waterfall plot. So you can see it is looking like a beautiful falling waterfall. It's a continuous type of waveform, right? So that is called as a waterfall plot. And even you can have one thing called as UV plot. You can have either a waterfall plot or UV plot. It is executing. Wait a second. I think the answer, you can see the graph. This is your UV. It is plotted on a UV scale. U is both U and V are normalized from -1 to 1. So it will give a better idea about the antenna lobes, or where are the major lobes, minor lobes. You can have this for a UV plot, and then you can plot the electric field and power. This is the electric field. Along the major lobe, you have maximum field. Along the minor lobe, you have minimum field. This is the electric field distribution of the antenna. Next one, beam width. Any antenna, you will find the beam width. Beam width, if the beam width is very, very narrow, it means the antenna is sending out a sharp beam. So see here the beam width. You have to beam width is 52 degrees. 52 degrees is very, very big. Degrees. 2 times your beam width is going to be the angle, so it is 104. How you get 52? 116 minus 64, you get 52. When you subtract the two angles, that is going to be 2 times that angle beam width. If you get only 64, 2 times 64 is beam width. When you get two different angles, the difference between the two angles is going to be the beam width of the antenna. This is how you visualize. Whatever parameters we have seen here in this particular example is all far field parameters. The far field means I'm going to measure the antenna parameters at some distance, at a longer distance from the point where the antenna is actually present.